Section 5.3, Elastic Collisions. An elastic collision is defined as a collision in which momentum and kinetic energy are both conserved. One common way to remember elastic collisions is to think of billiards. In the game of pool, strategies are based on the fact that the collisions between billiard balls are elastic, and the best players know that during these collisions, both momentum and kinetic energy are conserved. In an inelastic collision, it's one in which momentum is conserved, but kinetic energy is not conserved. We're going to look at perfectly elastic and inelastic collisions. A perfectly elastic collision, as I mentioned, is an ideal collision in which external forces are minimized, momentum is conserved, and kinetic energy is conserved. So we can see with these two equations, the initial momentum is equal to the final momentum, and the initial kinetic energy is equal to the final kinetic energy. Let's take a look at sample problem number 1, analyzing perfectly elastic collisions. Suppose you have two balls with different masses involved in a perfectly elastic collision. Ball 1 with mass 0.26 kilograms traveling at a velocity of 1.3 meters per second to the right, collides head-on with a stationary ball, ball 2, which has a mass of 0.15 kilograms. Determine the final velocities of both balls after the collision. We can start by writing down what's given in this question. We know that M1V1 initial plus M2V2 initial is equal to M1V final 1 plus M1V final 2. Now we know that billiard ball number 2 is initially at rest. So its initial momentum is 0. So the initial conditions simplify to M1 V initial 1 is equal to M1 V final 1 plus M2 V final 2. Now in this example, our job is to find V final 2 and V final 1. We have two unknown values. In order to solve with two unknown values, we're going to have to use substitution. So we're going to use this first equation, the conservation of momentum, as equation number 1, in which we're going to write V final 1 in terms of V final 2. So let's get V final 1 by itself. So we have M1 V final 1 is equal to M1 V initial 1 minus M2 V final 2. Then we'll divide both sides by M1. We can see in the first and second terms, the M1s will cancel out. So we're left with V final 1 is equal to V initial 1 minus M2 V final 2 over M1. And we actually have values for V1, M1, and M2. So we can sub in these values. We know that V final 1 is equal to 1.3 meters per second minus mass 2 is 0.15 kilograms. VF2 divided by mass 1, which is 0.26 kilograms. We can simplify 0.15 divided by 0.26, so we're left with 1.3 meters per second minus 0.58 V final 2. So we've written V final 1 in terms of V final 2. So that will allow us to substitute this value into our second equation. For equation number 2, we're going to use the law of conservation of kinetic energy to help us. And we're going to use this value, VF1 equals 1.3 meters per second minus 0.58 VF2, to help us solve for both unknowns. Equation 2. We know that the first ball is moving, M1, but the second ball is at rest. So we know that in the initial situation, only M1 has a kinetic energy equal to M1 half M1 V initial 1 squared. And in the final conditions, we know that this will be equal to, this total kinetic energy will be equal to the final kinetic energy of mass number 1, 1 half M1 V final 1 squared, plus 1 half M2 V final 2 squared. In order to simplify this, I'm going to multiply both sides by 2. When we do so, we'll be able to get rid of the 1 half in each term on both sides of the equation. So we're left with M1 V initial 1 squared is equal to M1 V final 1 squared plus M2 V final 2 squared. So we know V final 1 is equal to 1.3 meters per second minus 0.58 V final 2 squared. So we're going to substitute this value in for V final 1. We're going to put all other values that we know in as well. So M1 is 0.26 kilograms. V initial 1 is 1.3 meters per second squared. M1 is 0.26 kilograms, and we're going to put in 1.3 meters per second minus 0.58 VF2 in for V final 1. Don't forget to square this. Plus M2 V final 2. Just moving it over so we have room. Plus M2 V final 2 squared. We'll put in 0.15 kilograms for M2 times VF2 squared. So if you look at this equation, we've been able to get rid of one of the unknown variables. So our job will be to solve for VF2. We see VF2 appears in 2 spots. We can simplify. The left side equals 0.439. And then we're going to use the distributive property to multiply the 0.26 kilograms times everything inside the brackets. And I'm going to leave out the units just for simplicity. So we have 1.3 minus 0.58 VF squared, VF2, and we're going to square this. This is a difference of squares, and we're going to expand this where we square the first term, 1.3 squared. We multiply the 2 terms together and multiply by 2, and then square the final term. Hopefully you remember how to do this from previous years. When we do so, we get 1.69. And again, I'm leaving out the units. Minus 1.51 VF2 plus 0.34 VF2 squared. Plus 0.15 VF2. So we're one step closer to collecting like terms. First thing we have to do is multiply the 0.26 with everything inside the brackets. So we have 0.439 is equal to 0.439 minus 0.39 VF2 plus 0.88 VF2 squared plus 0.15 VF2 squared. So again, we're going to have to collect like terms and solve for VF2. We have 0.88 VF2 squared and 0.15 VF2 squared. I'm also going to bring this left side 0.439 over the equal sign. When you do, remember, it'll become negative. You can see that 0.439 minus 0.439 will be 0. So we end up with 0 equals negative 0.439 plus 0.439 minus 0.39 VF2 plus 0.88 plus 0.15. If you add those two up in your calculator, apologize, it should be 0.088 VF2. You end up with 0.24 VF2 squared. Simplifying this further, we have 0 equals negative 3.9 VF2 plus 0.24 VF2 squared. We're going to take the negative 0.39 VF2 and bring it over the equal sign. When we do, it becomes positive. And we'll do this in a way that you'll see helps us to solve for VF2. So we have 0.39 VF2 is equal to 0.24 VF2 squared. Divide both sides by VF2, reduces the VF2 on both sides. So we are left with 0.39 equals 0.24 VF2. So we can solve for VF2. It's equal to 0.39 divided by 0.24. If you punch this into your calculator, you'll end up with a value of 1.6 meters per second. We can now use this value of VF2 to solve for VF1. Up above, we said that VF1 was equal to 1.3 meters per second minus 0.58 times VF2. So we can sub in our newfound value for VF2. We get 1.3 meters per second minus 0.58 times 1.6 meters per second. If we punch this into our calculator, we end up with 0.35 meters per second. So the final velocity of billiard ball number 1 is 0.35 meters per second, and the final velocity of billiard ball 2 is 1.6 meters per second. Now we can try a perfectly inelastic collision. Remember that a perfectly inelastic collision is an ideal collision in which two objects stick together perfectly, so they have the same final velocity. In this situation, momentum is perfectly conserved, but kinetic energy is not conserved. We can rearrange the equations above, and with substitution, we have this equation for the final velocity of the pair of objects that are now stuck together. And you can see that Vf is equal to m1 vi1 plus m2 vi2 over m1 plus m2. So let's try sample problem number 1. Using this simplified equation for perfectly inelastic collisions. And remember, this happens because the two objects share the same final velocity. In sample problem number 1, two cars, a sport utility vehicle with a mass of 2,500 kilograms, and a compact model with a mass of 1,200 kilograms, are coasting at a constant velocity along a straight road. Their initial velocities are 40 meters per second west and 10 meters per second west, respectively. So the SUV is catching up to the compact car. When they collide, the cars lock bumpers. Let's assume no external forces exist along the direction of travel, and total momentum along X is conserved. Let's determine the final velocities of the cars just after the collision. I want to show you how, using the conservation of momentum, we can get to this simplified version of the equation up above. So we know that the initial momentum, m1 v initial 1, for object number 1, the SUV, plus the initial momentum of the compact SUV will be equal to m1 v final. And I'm going to draw v final in red, and you'll see why in a minute, plus m2, and again in red, v final. Since these two objects stick together, they'll share the same final velocity. So if we factor the final velocity on the right-hand side, we can simplify this as m1 v initial 1 plus m2 v initial 2 is equal to vf m1 plus m2. Dividing both sides by m1 plus m2, we get v final is equal to m1 v initial 1 plus m2 v initial 2 divided by m1 plus m2. And now we can sub and solve, because we've just been able to simplify the equation like we've shown above. We can use our values. M1 is 2,500 kilograms. The initial one is 40 meters per second west. Plus M2 is 1,200 kilograms with an initial speed of 10 meters per second west. Now keep in mind these are both collinear, so we'll be able to add them algebraically. Divided by M1 plus M2, so 2,500 kilograms for the SUV, plus 1,200 kilograms for the compact car. If we punch this into our calculator, we'll get a final velocity of the two cars stuck together. We get 3.0 times 10 to the power of 1 meters per second west. Therefore, the final velocity of the cars is 30 meters per second west. Let's move on to sample problem number 2. We have a child with a mass of 22 kilograms, and this child runs at a horizontal velocity of 4.2 meters per second forward and jumps onto a stationary rope swing of mass 2.6 kilograms. The child sticks on the rope swing and swings forward. In part A, we want to determine the horizontal velocity of the child plus the swing just after impact. We know that the child's momentum, m1v initial 1, plus the rope's initial momentum, m2v initial 2, will be conserved and is equal to m1v final 2. And in this case, the rope and the child will have the same final velocity, so I've written it in red. It's equal to m2 v final 2. So this statement shows the conservation of momentum, but m2, the rope, is initially at rest and has no initial velocity. So m2 v initial 2 will cancel out, and we are left with m1 v initial 1 is equal to v final, I'm factoring it out, m1 plus m2. So v final is equal to m1 v initial 1 divided by m1 plus m2. We can sub and solve. 22 kilograms, and an initial horizontal velocity of 4.2 meters per second forward, divided by m1 plus m2. That's 22 kilograms plus the rope swing is 2.6 kilograms. If we sub and solve, v final, the child and the rope swing will have a final velocity of 3.8 meters per second forward. That's right after the collision. Now in part B, we want to find out how high the child and the swing rise. Right after collision, the child will move forward on the rope swing, and the rope swing will arc and cause the child and the swing to move upward some height above the ground. So in part B, we want to determine this height. We know that the kinetic energy possessed by the child in the rope swing will be converted into gravitational potential energy as the child and the rope swing rise. So we can exchange this for the equations 1/2 m1 plus m2 v final squared is equal to m1 plus m2 g delta y. And we want to solve for delta y. So delta y is equal to 1/2 m1 plus m2 v2, or v squared rather, v final squared, divided by m1 plus m2 g. We can see that m1 plus m2 on the top and the bottom cancel each other out. So we are left with, I'm going to write this in a nice, simple, concise way, v squared over 2g. We can sub our values in. Delta y is equal to 3.8 meters per second forward squared divided by, in fact we don't need to put the direction because when we're talking about energy we're talking about scalar quantities, divided by 2 times 9.8 meters per second squared. Punch this into our calculator and we end up with a final height of 0.72 meters. Therefore the child in his rope swing will rise 0.72 meters above the initial height. Try practice problems on page 236, 238, and review questions on 239.